Hey, in this video, I'll be covering one important graph algorithm called depth first search. So depth first search has a lot of applications like pathfinding, detecting a cycle in a graph, topological sorting, and you name it. Also, DFS is going to form the base or the foundation for several interview questions which I'm going to be covering. So let's get started. So basically, I hope the screen is visible. So depth first search approach plus code, and the graph has been given. Also, the graph is an undirected graph consisting of nodes and edges, as you can see, right? So basically, a little terminologies I want to make it clear for those who are new to graphs. So basically, the red ones, the numbered ones, right, are called as or termed as nodes. So in this case, the nodes are 1, 2, 4, 3, and 5, and then 10 is also a node, right? And the blue lines are basically connectors. So what are connectors? So connectors are termed as edges, which kind of connect one node to the other node. So in this case, if you consider this connector, which I'm going to kind of cross mark in this 4 and 5, right? So this connector is kind of, or edge is kind of connecting 4 to 5, right? That's one terminology. Also, notice one thing, that if I have some node here, so n1, and I have node n2, and this is the representation. This means that I can go from node n1 to n2 and from n2 to n1. So I can go from n1 to n2 and vice versa. But what if I have a small arrow representation here, right? Then that means that I can go from n1 to n2, but not from n2 to n1. So this is kind of a directed edge. But do we have a directed edge? No, we have an undirected edge. So that's one of those terminologies I wanted you to be cleared of, right? So let's get started with the depth first search. So depth first search kind of in its own terms means we are going to be going in the depth first of whatever the representation is. In this case, our representation is graph. You kind of consider this as a graph of the cities, something like that, right? So in this case, what does the depth first means? So depth kind of means that I'm going to be going and exploring in depth one particular node until and unless I cannot go further, which means that I'll be not exploring, or I will stop exploring when I see that there are no neighbors, right? So in this case, what is a neighbor? So consider a node like 4, right? Consider a node like 4. So what is the neighbor of 4? The neighbor of 4 is 1 and 5, because from 4 I can go to 1 and I can go to 5, right? If I consider node 1, I can go from node 1 to node 2 and 4. So what are the neighbors of 1? The neighbors of 1 are 2 and 4, right? I hope the neighbors term is clear, okay? So let's get started with the approach. So I'm going to be maintaining one thing called stack here. So stack is a prerequisite which you can watch from any other video. So I'm going to write a stack here. Maybe I can cover the stack in some particular video. So stack is going to be a simple array kind of a thing, or an array kind of a data structure as of now. I'll be also maintaining one path data structure, and it's also going to be an array, right? And maybe that's it, right? I'll also maintain one set or an array. In your case, or in my case, I'll just maintain a set called visited, which will kind of keep track of the nodes which are visited, so that I don't visit a node, for example, 3 twice, right? That's illegal in my case. So I hope the representation is, let's see. So I'm going to be doing a depth first search starting at node 1. You can do a depth first search starting at any node, right? You're not restricted that you have to be starting a depth first search at node 1 itself. Just for a clear representation or explanation, I'm starting at 1. So I'm just going to do a DFS at node 1, right? So what is the process which I'm going to follow? So my current node, right? So I'll just push it into the stack as of now. So my current node is into the stack. Now what I'm going to do is I'm going to pick the lastmost node in the stack, which is unexplored, okay? The last node in the stack which is unexplored or not visited, okay? So what is the lastmost node as of now? Well, it's 1. So I'll just pick that, cross mark it, and put it in the path, and also the node which I just cross marked, I'll explore it. So what are the nodes which I can visit from 1? I can visit 2 and 4, right? So I'll just write 2 and 4 in the stack. As simple as that. Now again, I'll be visiting, or I'll be picking from stack the lastmost node which is kind of unvisited or unexplored. In this case, the lastmost node is 4, right? The lastmost node is 4. So what I'll do, I'll cross mark 4, I'll put it into the path, right? And then I'll kind of explore 4. So from 4 I can go to 5, right? So I'll just push 5 into the stack. As simple as that. No drama, right? Again, I'll just pick the lastmost node. So that's 5, right? Again, I'll just cross mark 5. I'll put it into the path. I'll explore 5 here, right? But I can see here that, well, 5 has no neighbors to explore. And this is the point where we have reached the maximum depth. As of now, we are considering this as the maximum depth. So maximum depth in our graph representation given in the diagram, right? So this is the kind of like the end point of a particular graph representation, right? In this case, 5, because it has no nodes to be explored or no neighbor nodes as of now. Well, it had 4, right? You might say, well, 5 has a neighbor node 4 and that's not an end, right? But hey, 4 has been visited, right? 4 has been cross marked here. So that's something which you have to consider. Now again, what I'll be picking from the stack is one node or the last node from the stack which is unexplored. So you might say that, well, I can pick 5, but 5 is explored or visited. You can pick 4. No, 4 has been visited. You can pick 2. Yes, you can pick 2 because 2 is the lastmost and is not visited. So I'll just cross mark 2 and put it into the path. As simple as that, right? It's a simple step-by-step process. Now, since I cross mark 2, I'll explore 2, right? That's what our agenda is. So from 2, we can go to 3 and 10, right? So I'll just go to 3 and 10, or maybe I can just write it in 10 or 3, right? It doesn't matter as of now. So I'll just write 3 and 10 just to be as random as possible. 50-50 chances, right? Now again, I'll pick 10 because here 10 is the lastmost node. I'll explore 10, but again, I can see that 10 has no neighbor nodes. So again, we have reached kind of one of those depths in the graph representation, right? So I'll just write 10 here, right? Because I cross marked it. Again, I'll be picking the lastmost node, which is unexplored or unvisited or not visited. I'm saying this again and again so that the algorithm kind of gets stuck into your head and you don't have to be worrying about it when you are writing the code, right? So again, I'll be cross marking 3. I'll write 3, but again, I'll be exploring 3 here, right? So is 3 having any neighbor nodes? You might say, well, 3 is having neighbor node 2, but is 2 not visited, but 2 is visited, right? So 2 has been visited. So 3 is currently having no neighbor nodes. So this is also one of those depths in the graph, right? Now this has been done. Well, our process has been finished. This is the depth first search traversal of the path of the graph representation. Let's kind of validate it if we are right or not. We are seeing there is the path called 1, 4 and 5. Let's just draw a one small line with maybe just depth, increase the font here. So 1, 4 and 5, right? We are kind of going like this. So have we not gone like in a depth first manner from starting at 1, which is our root node, or maybe if you consider 1 as the starting node. So from 1, I have gone till the depth. For example, in this case, it's 5. And then I'm going like this. So 2 and maybe 3, right? But in this case, we have gone to 10. So I can kind of draw it like this. So I have gone from 1 to 4, 4 to 5, and then backtrack to 4, 1, and then I've gone to 2 to 5, 2 to 10, right? And then again, I'll kind of backtrack, and I'll go to 3. So that's why we have 1, 4, 5, 2, 10, 3, right? So 1, 4, 5, 2, 10, 3. Again, you might be confused. Well, how is this path even making sense? Again, I'll be trying to explain the path one by one, right? So see, here's what the internal process is going to look like. So from 1, I'll be exploring in depth. So what I'll do, I'll just go in depth. So this is the path initially, right? So 1, 4 and 5. I hope this part is clear. Now, how is 2, 10 and 3 coming? Why am I not writing 1, 2, 10 and 3? Well, 1, 2, 10 and 3 won't make sense. But why am I writing 2, 10 and 3, right? So what is really happening is I'm going to go back from 5 to 4, right? I'm going to go back from 5 to 4 and check if is 4 having any other nodes to be visited, right? Or any other unvisited neighbor nodes. No, 4 is nothing. 4 is having no other like neighbor nodes which have not yet been visited. So I'll go to 1, right? So I'll go to 1. So from 1, I'll check that is there any neighbor node which has not yet been visited? Yes, there is one node. What is it? It's 2. So again, I'll just do a depth first search at 2. Well, here at this point, I can go either to 10, right? I can go either to 10 or I can go in this fashion to 3. It doesn't matter. Both of them are valid paths. In this case, I have gone from 2 to 10. So let's just explain it like that. So from again 1, I'll just go to 2 and then I'll go to 10. From 10, I'll kind of backtrack to 2, right? So I'll kind of backtrack or revisit that 2, but hey, we won't add that 2 into the path, right? So from 2 again, I'll check that is 2 having any neighbor nodes which has not yet been visited, right? Well, I can see that 2 is having one neighbor node 3, right? So I'll just do a depth first search from 2 till 3. That's it. So we have 1, 4 and 5. So 1, 4 and 5, and then 1 to 2, 2 to 10, and then 3. So 2 to 10 and to 3. Again, I don't have to be writing 1 here, right? That's not valid in our case. What are the other valid DFS traversals of this graph, right? There can be more than one DFS traversals, and that's true, right? So other traversals are maybe 1, 2, and 10. So I can just write 1, 2, and 10, and then 1 to 10. So from 2 to I can go to 3. So I can just write 3, and then I'll kind of backtrack up here, and then I'll just write 4 and 5. I'll just write 4 and 5, right? And I hope that makes sense. Again, there might be various. The more the larger the graph is, like, so for example, I'm telling you that if you have a lot of edges and lot of nodes, or even a lot of edges, then we can have more number of DFS traversals of a particular graph representation, right? So what are the various data structures which we are going to be implementing? So we are going to be using a stack, right? We are going to be using a set for maybe a visited node kind of a thing, and then maybe you will use an array called path. Also, notice that to represent the entire graph, right? To represent the entire graph, we have to be using, maybe we can use any of those 2 important graph representation techniques, right? And they are namely adjacency list and adjacency matrix. So in this case, I can use adjacency list, and it's going to be, I'll be implementing it using dictionary in Python. So the code is going to be written in Python here. So I'm just going to write the code in Python 3, right? It might Python 3.4, 5, 6, 7, 8, 9, whatever the case is, so that you can be able to, you can easily convert the Python code into your favorite programming language, C++, C, Java, and if you write it in Python, then it's a bingo. So let's get started with the thing. So I'll just kind of check, yeah, it's been in the recorded process. I'll kind of start with the Visual Studio Code. So what I'll be doing is, I'll be creating one, maybe like I'll just kind of import few stuffs here. So from collections, I'll import default dictionary, right? And then maybe I can just write if name. These are some of the few prerequisites which need to be added here, right? Now this has been done. I'll be creating one graph, right? So how do I do that? Let's see. So I'll just write graph this much, right? So basically my graph is going to be a dictionary, right? So I'll just write default dictionary, and it's going to be, the keys are going to be the nodes, and the values are going to be a list of nodes, right? Because I'm going to be going from one node to several neighbor nodes. So kind of I will have them in the list. So default dict and list, right? And I hope that makes sense. Now that we have this, we'll kind of have some inputs here. So what are the inputs going to be looking like? Well, I'll just look at whatever the representation was and kind of defer the input from there. So in this case, 1 is connected to 2 and 4. So I'll just write 1 is connected to 2 and 1 is connected to 4, right? 2 is connected to 10 and 3. So 2 is connected to 10 and 2 is also connected to 3, and 4 is connected to 5. 4 is connected to 5. So I have 1, 2, 3, 4, 5. 5 of those inputs are something which we have, right? So I'll just kind of write this when I'm trying to get the input, right? How many edges do we have? We have 1, 2, 3, 4, 5 edges. And notice that the number of edges are the number of inputs. So 1, 2, 3, 4, 5. 5 inputs, right? Because hey, we are representing the inputs in the form of edges, right? Yeah. So I'll just kind of write a for loop here. So for I in range 5, because I'm just considering the example. In your case, you will be just asked to complete a function, right? I'm just building the writing the whole code from scratch. So I'll just consider U and V, which are the nodes. So from U, I'll go to V, or maybe I can just write node 1 and node 2, right? And I'll kind of input it. So map int comma input dot split, and I hope that makes sense. And now in the graph, right? In the graph, I'll just write graph node 1 dot append. So kind of it appends the node 2 value into the node 1 representation here. And now what I'll be doing is graph node 2 dot append node, okay, this should be node 2 here, my bad. So this should be node 2 and this should be node 1, right? Why am I writing it twice? Well, I'm kind of making sure that we have connections from both the sides. from node 1 till node 2 and from node 2 till node 1. Why? Because again, I have mentioned this in the beginning that this is an undirected graph. If this was a directed graph, I would have avoided this line. I would have avoided this line here. As simple as that. But since it's an undirected graph, I have to make connections from both the end, right? I'll check if it's in the recording process. Perfect. Now I'll be maintaining one set here, visited set, right? And in my case, I'm considering the start node, right? My start node is 1 in my case, right? I'm just considering the start node as 1, as simple as that. I'll be having one stack here, right? I'll be having one stack here. And what should I be having in the stack? In the stack, I'll be maybe having the start node here, right? So I'll be having the 1, right? Which is nothing but the stack node. Also, I'll push or I'll add 1 or the start node to my visited, because I don't want to visit my start node again, right? So visited.add my start node, which is 1 in this case. Also, I'll be maintaining one array called path. And again, this is something I have mentioned in the board kind of a thing, right? So basically, I mentions about stack, set, path, and the graph representation has already been done. So that's a bingo. So these are the few data structures which I mentioned and which I have just implemented, right? Now, my approach is going to be looking like this. While my stack is not empty, right? So how do I do that? So I can just simply write while stack in my case, or I can write while length stack, right? Or I can write while length stack is greater than 0, right? And this kind of sounds fair enough. So I'll just write while length stack is greater than 0. My current node is going to be the lastmost element in the stack, or the lastmost node in the stack. Okay. Now that this has been done, I'll try to explore the current node, right? And before I do that, I'll make sure to add my current node to the path. So I'll just kind of add current node to the path, right? As simple as that. So path dot append, my current node should be this much, and then I'll try to explore the current node. How do I do that? I'll just run a for loop here. So for neighbor node, make sure you spend time to name your variables properly. So for neighbor node, in the graph representation of current node, right? As simple as that. So I'm kind of exploring the current node. What if I say that, hey, I'm at node 2, right? If I'm a node 2, what are my neighbor nodes? My neighbor nodes are 3 and 10. So that's what I'm going to be exploring here, right? I'll check that if my neighbor node is not in visited, right? Or I don't really need to write is here. So if I'm just writing if neighbor node not in visited, that will also make sense. Then in that case, visited dot add neighbor node, right? So this should be neighbor node. And then I'll append to the stack the node value, which is the neighbor node itself, right? So that's neighbor node itself, right? And this is it, right? This is it. This is the thing which we are looking forward to, right? And what will happen is this, in an iterative format, every node will be covered, and at the end of the day, my stack will be empty. And when my stack is empty, this condition won't satisfy, right? This condition won't be valid while length stack is greater than 0, right? So at the end of the day, we can just simply print the path here. So I can just kind of write here, print path, right? Or to be in a more fashion manner, I'll just write for I in range length path, right? So that's kind of taking the length of the path, entire length of the path, and then I'll just print path of I, and I'll just have a few representations here. Yeah, that makes sense. I'll also check that if I is equal to length path minus 1, because hey, that's the end, so I won't really be having that arrow symbol, right, pointing to the other node. So I'll just have path of I. Else I'll be having this, right? And I think this should do for the coding part. I'll try to execute this and see if there is an error, right? So I'll just write Python 3. My file name is dfs.py. Again, I'm using Visual Studio Code, right? I think I should be inputting some values here, right? So what are my values? Again, the values I can retrieve it from here. 1, 2, 1, 4, right? So I'll just write 1, 2, 1 and 4. Then we had 2, 10, 2, 3, right? So that's 2 and 10, that's 2 and 3, and I think there should be one more. Yeah, we have 4 and 5, right? So we have 4 and 5. I'll just press enter. Am I missing out on something? Let's see. Okay, let me just try to give one more thing here. 1 and 2, 1 and 2, 1 and 2. Okay, I think there's some error here, so I'll just kind of correct from here. If name is main, graph is this much. For I in range, node 1, node 2 is map this much, and then maybe I can try to do this, right? So am I missing out on something? Am I? Okay, that makes sense. Okay, so basically what we did was, we are kind of taking the current node in the stack, right? We are taking the current node in the stack, and we are also kind of appending it or adding it to the visited, right? So what I'll be doing is, after taking the current node, I'll try to remove that node from the stack. So what happened here is basically the while loop was not ending at all, right? So in this case, what I'll be doing is stack.pop. In Python, if I just write stack.pop, it means that, hey, you are removing the last most element from the stack. Or you can kind of use a negative indexing here. In Python, you have a negative indexing facility as well. So anything would do fine. So I'll just kind of write stack.pop here, and I'll kind of save it. And let's see if, I'll just kind of save it here, Control S. And we have one problem here. Okay, I kind of wrote something here, so I'll just remove it. Okay, I think I stopped the video. No, it's in the process. Let's go. I think I'll just save this thing here, debug console and terminal, and I'll just clear this enough. I'll just write Python 3 and then my file name dfs.py. I'll again just take a look at my inputs. 1, 2, 1, 4, 2, 10, right? So that's 1, 2, 1, 4, 2 and 10. We had 2 and 3, and then we had 4 and 5, right? So hey, we have the path here, 1, 4, 5, 2, 3, 10, right? In our case, what was the path? I'll just check that. So in our case, we had a path like 1, 4, 5, 2, 10, 3. But hey, in our output, we have 1, 4, 5, 2, 3 and 10 instead of 2, 10 and 3, right? So that's it. And this was all about the DFS, right? And again, we had some problems which you might face it, right? You might also face some problem like the while loop is not ending, or you have not written proper number here. So for example, if you write 6 here, right? If you write 6 here, but you are taking in 5 inputs, again, that's wrong. And again, I just did a small mistake here. The mistake was I was not popping the element from the stack. So I'll just kind of write it in comments. So pop the last most element or the current node, which is the last most element, right? That's it. And I think this video was helpful. And I'll be uploading various other videos which have applications of DFS. Also, the breadth first search, which is kind of another graph algorithm, will be covered in the upcoming videos. So thank you for watching, and we'll meet in the next video.